about the X, is there a formula for X written before؟ لأنه previously أخذناها في term 1 بس نسيتها personally. Why
Yes.
if 100% دغري قلنا إنه it's
Okay.
saturated vapor؟
Yeah, I will remind you of the definition of X. X is the one we talked about in the slides today. So what is the idea about X? Going back to the course here, the material, okay?
Yes.
If you have the curve here, for example, okay? If I give you, you know, from the tables of thermodynamics, you can get the following. You can get everything called, for example, VF, HF. It's correspond to saturated liquid. It corresponds to X equals 0. And everything we name VG, HG correspond to the saturated vapor. Okay?
يعني بطل فيها liquid حتى. Okay,
if you have any, this is why, because we said here quality is 100%. So X is equal to 1. This corresponds to the vapor state. Okay? Now, if I give you any X in between, if I tell you X equal 90, you apply the formula. You can say
liquid and vapor بيكون فيه.
Okay. So بيكون فيه portion of vapor, portion of fluid, and then you apply the following rule to find the property. So for example, if you search for enthalpy, you say that enthalpy is equal to 1 minus XHF plus XHG. Or another method is to say it's HF plus HFG times F. Because if you take it into factor, you get G minus F times F. Okay?
Okay, great. I just forgot the formula. That's why I asked. Thank you, doctor.
It's fine. Okay. So now, going back to our problem, we determined the inlet state and outlet state of our turbine. So all we have to do now is to go back to our relation. V, as we said, all is given. We found H inlet and H outlet from tables. So now if we replace in our first law of thermodynamics, the only unknown will be what? It will be the work. And as expected, the work will give you a positive result because the turbine is providing work to outside. Okay? Any question for this problem? So let us move to another problem. For the pump, we will consider now a pump. A small liquid water pump is located 15 meters down in a well, taking water in a 10 degrees, 90 kilopascal at a rate of 1.5 kilogram per second. The exit line is a pipe of diameter 0.04 meter that goes up to a receiver tank containing a gauge pressure of 400 kilopascal. Assume the process is adiabatic with the same inlet and exit velocities and the water stays at 10 degrees. Find the required pump work. Okay, so here we should look at all information given. So first, the inlet condition is given 10 degrees, 90 kilopascal. This will allow us to find what? To find H water at inlet. So we go to tables and we search for H water at inlet. Okay. Now, at the final state, we know that the pressure is now much higher due to the pumping effect. The pressure is 400 kilopascal and also for at 10 degrees. So from here we can get H water at outlet. Okay. And here we should pay attention that we should take into consideration potential energy because look, they gave you the elevation, the final elevation. So when they give you information about elevations, use the potential energy in the formula. And they said that we have same inlet and exit velocities, so we can, so no variation in kinetic energy from this information. Okay. Now I will write the first law of thermodynamics on my system. On my system of pump and reservoir. So I have that. Writing my formula, okay? We know that, as I said, the kinetic energy is not varying. You have Zn and Z out, you can take a reference line, okay? So you can take your pump as reference because I told you that the pump is at 15 meter below the reservoir of water. So if I take my reference here, this will correspond to Z inlet equal to 0. So Zn is 0 and Z out here is equal to 15. Okay, so this is Z out equals to 15. Now, going back to my first law, as we said, we still need to find H in and H out. Okay, now what we can do here, because it's a liquid, as I told you before, okay, because it's a liquid, you can use the following formula for the pump, because the work for a pump here, when you have a liquid, you can find the difference in enthalpy according to this relation, which is H out equal to Hn plus delta P times V, where V is the specific volume, okay? And because, as I told you, for a liquid, we assume that the variation of specific volume is very small, so we can find, we can use this relation between H exit and H inlet, okay? So, replacing in the energy equation, in this case, we can in this case, by replacing here, we just need the difference between H inlet and H outlet. No need to find each one. Okay, why? Because look, when you take it to the other side, you will have H inlet minus H outlet. So what you care about is the difference. Okay, and the difference between H in and H out is P exit minus P inlet times V. Okay, so you can here deduce that.
Doctor,
Yes. Yes,
we can't find the enthalpies from the tables.
we can. Of course, we can. Okay. So
Okay.
of course we can. But if you want, this is another method. Okay. Anyway, you still need the tables. Why? You still need the tables because you should find what? You should find the value of V, which is the specific weight. Okay. So to find the specific weight here, because the temperature is 10 degrees, we can go to the tables, okay, and find the specific weight at 10 degrees. Let us try it. So these are the fundamental, these are the tables, okay.
بس
If I go
البريشر بيصير باسكال ما هيك او كيلو باسكال.
kilo pressure, it's here. The pressure is varying. Initially, it is
بس انا بالكالكوليشنز
90 kilopascal. After it is 400 kilopascal. Look, it is true that, as you are saying, the pressure is different. So of course the volume will little bit vary. But because it's a liquid, we can see it together. We can search for it. The variation in V is very small. So you can demonstrate, if you go to the thermodynamic tables, you can demonstrate that the difference is really small. This is why I can make the assumption that delta H is V delta P. And if you want, let us verify it together. Okay, so you have 90 kilopascal and 400 kilopascal. Let us go to a table in the compressed liquid and look what is the value of V for 90 kilopascal and for 400 kilopascal. Okay, let us do it. But first, let us find V from this table. If you go to the saturated water table, your temperature is 10 degrees. So now you should not go to, if you want here, if we go to the pressure entry, what are our pressure? We have two pressures, okay? What is the first one? I think 90 and 400 kilopascal. Let me make sure. It's 90 and 400 kilopascal, okay? Let us see in this table if V is varying. 90, it's nearly close to, it's between 100 and, but look, I will not look in this table because here I have enthalpy and entropy, and what I need is the specific volume. So I should go a little bit upward to have, yes, here I have the specific volume. So if I choose nearly 100 kilopascal, okay, look, 100 kilopascal is nearly between these two. So as you can see, my value is between 0.001037 and 0.001043. I can do interpolation and find at 90 what is the specific volume. Now if I look at 400, look at the 400 value, and you will see that it is really very close. So for 400 kilopascal, what is your, this is your specific volume, 0.001084. So the increase is nearly negligible. Okay, so it was nearly, it's less than 1%. Okay, in the order, no, not less than 1%, maybe let's say it's 10.4 and 10.8, so 0.4 over 10. Okay, nearly 4% if you want. Okay, still negligible increase. So the increase in specific volume is very small, much smaller than 10%. Okay, so we can say that it's less than 5%. So we can neglect this variation and we can treat it as constant V. Okay, now if you want to be very, very accurate, you can go to the compressed liquid tables. Let us see them together. So we will look at the compressed. Maybe they are below. Look, from table B1 we start. For the first table, they give you saturated water. You have several tables for saturated water. Some tables are with temperature entry and others are for pressure entry. So we are still in saturated water. I go down. Now I have pressure entry. After this, I'm still in the saturated tables. Now I have the superheated tables, and below I should have the compressed liquid. Okay, I should have the compressed liquid tables. Okay, so now for the compressed liquid tables, you can find the value of H if you want. Okay, so here, for example, what are your pressures? Your pressures are 90 kilopascal and 400 kilopascal. So let me see if we can find them. Okay, 1 second. So let us go down. So here we are starting the compressed liquid. Look, we start the compressed liquid starting from 500 kilopascal. Why we do this? Because we consider that below 500 kilopascal, we can approximate the state as saturated liquid. Okay, because the variation is really, really small. This is why, since in the compressed tables we don't have what is happening for pressures lower than 400 kilopascal, lower than 500 kilopascal. So in our case, where we have 490 kilopascal, we will use the saturated table and we will take the value from the saturated liquid. Okay, because as I told you, the compressed liquid tables are given above a certain pressure, whereas I consider that the compressing effect is would really affect the values of enthalpy, energy, etc. But below these pressures, I consider we can treat the properties are very close to the saturated liquid, so no need to use the compressed tables. Okay, is this clear? So here, if you want to use the tables to get H1 and H2, then you should use the saturated tables, which are here. And you should look at the pressure entry. You have 40 kilopascal and 90 kilopascal and 400 kilopascal. So this is the corresponding table. So you can go to 90 kilopascal. It's nearly here. 90 kilopascal. It's between 75 and 100. So this is, you should look at HF, the saturated liquid. Then you will do interpolation and find H in between. So it's nearly 400. Okay, maybe 403, 404. So nearly in the 400 values and kilojoule per kilogram. And for 400 kilopascal, the exit at the exit stage, your value of HF is here. It's 604.73. So you can directly say that I will do H2 minus H1. Okay, or if you want, as they told you, we can use V times delta P. Try to do both. You will get nearly the same result for both methods. Okay. So here it's nearly 604 minus 404, and it's very close to 200 kilojoule per kilogram. Okay. So if we can compare here with the value, if you do P delta V, try to do it. Okay. Try to do here. You have nearly 300 minus 90, so it's 200. 210. Okay, and no, it's 500 minus 90, so 410, and do times this ratio and compare with P exit minus P inlet times V. Okay, with H exit minus H inlet, you should have nearly the same result. Okay, so now once we replace in the equation, okay, we can get the only unknown here, which is the work of the turbine, the work of the pump, sorry. And also, as expected, because it's a pump, you will end up with a negative result because the pump take work from outside and will not produce any work. This is why it is a negative work. Okay, any question on this problem? So let us move to another one. And I posted for you, I will post for you, not yet, but I will. I'll post for you several problems similar to this so you can practice on them and use a thermodynamic table. So I will post soon a link for the book, and I will post problems on chapter 3. I already posted problem on chapter 2, so please try to solve them.
Okay, thank you, doctor.
Okay. Now, concerning the efficiency of a Carnot cycle, derive the expression of Carnot cycle efficiency function of T hot and T cold. Okay, so in this session we have seen what is the Carnot cycle. It's operating at two isotherms, so two constant temperatures, and two adiabatic where we don't have heat loss. Okay, so constant entropy. And we want to find its efficiency function of temperatures. Okay, I want to give you an additional note. We said before that the total work of a closed cycle can be calculated by integral PDV. Okay, and we said also that if it's a moving boundary, we use integral PDV, and if it is a fluid circulating in our system, we use minus integral VdP. Okay, but at the end, both represent the area under the curve P function of volume or V function of P. Okay, now if we consider another possibility to calculate the work is the following: is integral TdS. Okay, so if you want, this is another formula which allow us to calculate the work of a cycle, and it represents the area under the TS graph. So if I draw T function of S, the area limited by the curve will represent the work. And in a similar way, if I draw P function of V, the area inside the curve is also the work. So the work can be calculated graphically from a PV graph or from a TS graph. Okay, so here it is very easy to calculate integral TdS because it represents the area of a rectangle. Okay, if you look at this graph, you can say that W is the area under the graph. So the work of the Carnot cycle is equal to the area limited by the graph. And how I can calculate it here in a simple way? You should multiply the height times the width. Okay, so the work is given by W is equal to T, the width is equal to S2 minus S1, S2 minus S1, delta S. Okay, and the width is T hot minus T cold, so times TH minus TC. Okay, this is the expression of the work. Now, if you want to calculate Q hot, Q inlet, which is called Q hot, and Q outlet, which is called Q cold, QC, how to calculate them? For heat, okay, for heat, Q is given by also, pay attention for something here when I say integral TdS over the whole cycle, okay? So W equal to integral TdS over the whole cycle. Now, if I want to get just QH, Q hot is the heat provided in this phase here. How can I calculate it? So for QH that is coming in, I can say that QH is integral TdS only from this point to this one. So when I move, QH is given during this phase. When I move from this point to this one, okay? So Q hot that is provided to my system. For Q also, you can compute it in any phase, okay? In any phase, you can compute Q. By definition, Q is computed not only for a closed cycle, for any small phase I take, you can compute it by integral TdS. But why for the work it should be a closed cycle? Because in a closed cycle, total work equals total heat, okay? So, and the total heat is always integral TdS in case of one phase or case of a cycle. This is why for the whole cycle, total Q equal to total W equal to total integral TdS. But if I take just one phase, for example here, this phase where I have heating, then I can only say that in this phase Q is integral TdS and not work, okay? So pay attention for this information. And I will integrate from point 1, so integration from point 1 to point 2, from 1 to 2. Okay, but as you can see here, the temperature during this phase is constant, which will simplify a lot the integration, because since it's a constant, I can take it outside of the integration and I get equal to T times what? Times delta S, which is S2. And of course it's T hot because I am at the higher temperature. So it's T hot S2 minus S1. Okay, now what is the definition of efficiency? Efficiency is work over Q inlet, okay, Qn. So I can say that efficiency is equal to what was the total work, W net if you want, net work, okay. The net work was the area limited by the curve, so the net work was delta S, S2 minus S1, S2 minus S1 times delta T, which is TH minus TC, okay? And divided by Q, I will replace Q by its value, TH times S2 minus S1. So as you can see here, S2 minus S1 will be simplified, and I will get, what is the expression of my efficiency? My efficiency is equal to TH minus TC over TH, which is 1 minus T cold over T hot. So I derived in this way the expression of efficiency of a Carnot cycle, function of TC and TH. Okay? Now, who can tell me how can I calculate QC, the rejected heat at the condenser level?
It's the same way TC times S2 minus
Very good. It's the same way as I calculated QH. I can say that QC okay? But I will integrate here from 2 to 1, okay? Because from 2 to 1, I am, if you want, because already they put Q out, you know it's out, then you can put it as a positive value. But in general, if you don't know if I'm losing or gaining heat, you can just compute it as Q C equals to integral TdS from 2 to 1. So it's now from 2 to 1, which is equal to Tc times S1 minus S2. And as you can see, it's a negative result. Why? Because we are losing heat. This is why they considered that the arrow is outside. So when you put the arrow outside, then you can put near to it a positive value because you already know that it's going out. And for the work, you put QH minus QC. Okay? But if you calculate it as an algebraic value, it will be negative. Then you put here W is QH plus QC, and QC you count it as negative. Okay? So here, another method if you want to find W, other than the area under the curve, you can say simply that the network, okay, W net is equal to sum of Q, which is equal to Q hot, Q H, and here they put minus QC as I told you because they considered here the absolute value. Okay, so it will be then equal to, if you take S2 minus S1 into factor, if you take S2 minus S1 into factor, then you get times TH minus TC, which is the same result you obtained previously when you found the area under the curve. Okay, because it's equivalent. This method and the first method will give you the same result. Okay, and if you want another way to do the analysis, QC represents this area, the area under TC. Okay, and it's a negative Q because it's loosed by the system, while QH is integral TdS below this line. So this is QH, the whole area. And as you know, the network is the total heat, is equal to the total heat. So it's equal to QH minus QC. This is why if you subtract the big area and you subtract from it the small area, what do you get as work, as network? The difference between them is this part. Okay? So here you can see all details of calculation. As we said, the efficiency is defined as work over QH, which is QH minus QC over QH, which is 1 minus Q cold over Q hot. So you should now compute, this is another method here. You should compute Q cold and Q hot. If you compute Q hot, it's TH delta S, and Q cold, it's TC delta S. So when you do the ratio, you will get efficiency equal to 1 minus T cold over T hot, which is the same result we obtained to gas. So as you can see, we have several methods which will always end up with the same result. Okay? Let us start to do a new problem. So until now, we have worked with separate components. What will happen in a steam power plant is that we have several components at the same time and the fluid is circulating between them. Okay? So the other problems were a preparation for this one. Consider the simple steam power plant shown in the figure. The following data are given. So as you can see, this is the power plant. The power plant is very close to what we have seen together. What are the elements? You have a turbine to deliver work. You have a condenser to cool your fluid. You have to be able to be pumped because when it will go through the pump, it should be in the liquid form. This is why you need to cool it. Once it enters the pumps, it will increase its pressure. It will be ready to go into the boiler. The boiler will heat it, and then it will go to the turbine, and the cycle will be repeated. In general, we use the piping lines that are joining the different components. In general, they are well insulated in a way to not lose heat. Okay, but in this problem, they told us that for the line between the boiler and the turbine, we have some losses. Okay, so here they told us that we have some losses along this pipeline. So we should also, this is, we should add a second stage, a fifth stage if you want. In addition to stage 1, 2, 3, 4, we have a certain stage where we lose heat when we go from the boiler to the turbine. And this should be taken into consideration in our calculations. Okay, so let us now see what are the given. For the given, they gave us the state leaving the boiler, okay, 2 megapascal and 300 degrees. Now, always, you can predict the state. Because it's a boiler, at the exit from the boiler, what do you expect to have? So in general, a boiler will heat my steam, okay? So it will be, in general, it will be in the superheated region, okay? So you can estimate, and anyway, you can verify your assumption. This assumption, you can verify it after when you go to your tables. So I will say that for the boiler here, I estimate that I am in the superheated region, okay? When I leave the boiler, it's superheated. Okay, now let us move to the second condition for the turbine. For the turbine, what did they give me? They gave me also the pressure and temperature. Now, look, for when entering the turbine, also I can assume it's a superheated state, okay? Because in general, through the turbine, I will have, if you want, I will, at the exit of the turbine, I might end with a certain quality, but the quality should be very close to 100%. So you can say that always when entering the turbine, I should be still in the superheated region to work well. Okay, so I will assume that leaving the boiler and entering the boiler, I have superheated states, and I will verify this because I know the temperature and the pressure. Now, as you can see here, at the exit of the turbine, they gave me the quality. So they told me that the quality is 90%. So now for this state, I will use the saturated tables. Okay? The saturated tables, knowing the quality X, I can find what are the corresponding H, as we will see how. And finally, they gave me also the state leaving the condenser and entering the pump. So here I can, in general, the state is saturated liquid, okay? And I can verify this, okay? So in general, it is saturated liquid, and we will see together if it is or not, okay? And plus, they gave me another information. They gave me the pump work, okay? This information can help me to find an unknown enthalpy, okay? So it's an important information that can be used in the problem. So now, as a first step, let us find together the different enthalpies, okay? So let us go to the figure and we'll stick to the names given. So state 1 is at the exit of the boiler. So as we said, at the boiler exit, we estimated to have superheat state, and they gave us that the pressure is 2 megapascal and 300 degrees. So we will try to go to superheated tables, and we will search for 2 megapascal or 2000 kilopascal and 300 degrees. Okay, and as you can see, it's clear that the saturated temperature for 2000 kilopascal is 212, which is lower than 300 degrees. So of course we are in the superheated state. And if we take the value of H, it is 3023.50. Now, so we are done with H of state 1. Okay, now we move to H2. 2 is the point at the inlet of the turbine. Okay, the point at the inlet of the turbine is characterized by 1.9 megapascal and 290 degrees. So also we will try to go to superheated tables. Now, if you go to superheated tables, you don't have the pressure of 1090 kilopascal, which corresponds to 1.9 megapascal. So what should you do? You should do interpolation. Okay, how to do it? In these tables, you have values for pressure of 1080 kilopascal, and you have values for 2000 kilopascal. And since you want the value for 1900 kilopascal, then what you should do, you should find what is H in this table and what is H in this table. Then you should take the, here you take the middle value, because 1900 is just at the middle between 1800 and 2000. Okay, and if it's not in the middle, if I give you, for example, 1950 kilopascal, then also you do another interpolation. Okay, now what is a little bit, it will take a lot of time because also the temperature is 290. So you should do also interpolation between 250 and 300. So here the only difficulty is that you have to do several interpolations. So first you have to do an interpolation to get H at 290 here, then a second interpolation to get H at 290 there. So let me remind you how to do the interpolation. So I need to find at 290. So just you put it like a small table. You write at 250 corresponds to 2910, 2910.96. Okay, and 300 corresponds to 3029.21. Okay, and I want to find what is the corresponding value for 290. Since I'm doing a linear interpolation, so I have a constant slope. Okay, so I can write that, for example, 290 minus 250 over, so here let me put brackets. Okay. Please, the session will nearly end. If you want, we can open a new session. Can we open a new session to continue this problem, or to try, or you try to do it and we continue next time?
أحسن if you try to do it نعملها next time
Okay.
إنه
Okay.
Yes.
Please try to do it. Try to do it on yourself, and I will continue to solve it next time. Okay. So I will continue as much as possible. So here 300 minus 250 equals to, from the other side, you want to find H at 90. So it's H minus, what is H at 250? It's 2910.96 over H at 300, which is 3029.21, and minus H at 250, which is 29.